Hi everybody. So this is the first lesson of the 2-week hiatus that we're taking as a result of the COVID-19 epidemic. This first lesson is going to be a pretty short one. It's not going to be very long. It's also not going to be too complicated. Its objective is pretty narrow. It deals with the inverse trig functions. Not only are we going to be reviewing the derivatives of those inverse trig functions, we're also going to be looking at how do we find functions whose antiderivatives are inverse trig functions. So once again, it's going to be short. It's going to be sweet and simple. It's not going to be very long. I will ideally post some extra practice for you to try out too. So let's get to it. So first, once again, the objective, as I said before, is very narrow. I can use the inverse trig functions to evaluate certain integrals. So that's the only thing we're going to be focusing on in this lesson. So first off, to review some of the derivatives of the inverse trig function. So the first one, the derivative of inverse sine is equal to 1 over the square root of 1 minus x squared. The derivative of inverse tangent is 1 over 1 plus x squared. And then the derivative of secant inverse is 1 over the quantity x times the square root of the quantity x squared minus 1. Now, there's a reason why I only recap these three. You might be wondering, well, where's the inverse cosine derivative? Where's the inverse cosecant, inverse cotangent? In the last, I want to say 20 or 20 plus years on the AP exam, these are the only three trig antiderivatives that you'll see. So for that reason, these are the only three I will cover. The steps that we're going to follow in these three practice problems, they're a good outline of what you would follow given any inverse trig antiderivative. But the chances of you seeing anything other than these three on the AP exam are very low. Honestly, the inverse sine and the inverse tangent are the ones that you'll most likely see. Even the inverse secant one is pretty rare. I believe last year, at least on the practice exam, I know that there was an inverse tangent problem. I know that. But once again, these inverse trig functions are not going to be something you'll see a lot of. In a best case scenario, there's probably going to be one question involving them. Otherwise, I wouldn't freak out too much about this is going to destroy my grade, but we will be covering it to make sure that you guys do get some exposure to it, and hopefully in the future you do remember it. And we move on to our first example. So example 1. So find each of the following integrals. So the first one, the integral of dx over the radical 4 minus x squared. So first, let's rewrite this, just so that it's a little bit more clear, as the integral of 1 over radical 4 minus x squared dx. All right, so how do we know this is an inverse trig? Well, it should be a pretty good giveaway. The main thing you want to look at is the fact that we have a square root, and inside the square root, we also have the difference between a constant and an x squared. Because if you look back at what the derivative of inverse sine is, for example, it's 1 over the square root of 1 minus x squared. Now, in this problem, we have 1 over the square root of 4 minus x squared. So it's pretty darn close to what it should be looking like. So that should be a giveaway that this is an inverse sine antiderivative, inverse sine antiderivative. Now, well, what do we have to do, or how do we have to do this? Well, once again, the derivative of inverse sine is 1 over the square root of 1 minus x squared. So we have this 4 here. So what are we going to do? Well, we want to turn this 4 into a 1. All right, so that's going to be your main focus. You want to turn this 4 into a 1. So what we're going to do here is we're going to factor out a 4 from 4 minus x squared, all right? So we're going to rewrite this, as the integral of 1 over the square root. I'm going to factor out a 4 here. So the 4 now becomes a 1, and the x squared, if you factor out a 4, just becomes x squared over 4. Okay, so that's going to be your first step. You want that first term in there to be a 1. It was a 4, so we made it a 1. Now, if you notice here, we have a square root of 4. We have a square root of 4. Square root of 4. So we're going to turn that square root of 4 into a 2, just to remove the constant out of the integral. So we're going to rewrite this as square root of 1 over 2 the square root of 1 minus x squared over 4. All right? So all we did here was we just turned this square root of 4 into a 2. Excuse me. So we turned the square root of 4 into a 2. All right. So we made some progress, except now that we have x squared over 4. Now, the trick here is, okay, if going back, we want this to be something squared. All right? We want this to be something squared. So quantity squared, that's it. Now what we have is a quantity squared over 4. So what we're going to do here is we're going to turn this, I'm going to write it up here. We're going to turn x squared over 4 into x over 2 squared. So x squared is x squared, and 2 squared is 4. So we're going in reverse. We're basically rewriting x squared over 4 into just some kind of quantity squared. All right. So we're turning this, right? This is our quantity that we want to square it as. Okay. So we're going to do now the integral of 1 over 2 the square root of 1 minus the quantity x over 2 squared. Excuse me. All right. So at this point, so we have a 1 over 2. So I'm going to rewrite the 1 over 2 to the front of the equation. So we have the integral of 1/2 times 1 over the square root of 1 minus x over 2 squared dx. So I just moved the 1/2 to the front. Excuse me. Now, the problem is, though, and I know this is getting complicated, we want x squared, but we have x over 2 squared. So this is where we have to use the u substitution. So we're going to set u is equal to x over 2. So the derivative of this is just 1/2. So that means if I were to rewrite this in terms of dx, it'd be 2 du is equal to dx. So now we're going to make these substitutions, right? So we're going to put u in for x over 2, and we're going to put 2 du in for in for dx. Sorry, I put an extra 2 over here. It should just be dx. All right? So let's see what we end up with. So we have the integral of 1/2 times 1 over the square root of 1 minus u squared times 2 du. Okay, so we replace the x over 2 with the u, and we replace the dx with the 2 du. Now, hopefully you should see some cancellation here. This 2 cancels out this 1/2. So all we're left with now is the integral of 1 over radical 1 minus u squared du. Now, if we look back, that is exactly what the antiderivative of that is exactly what the derivative of inverse sine is. So if we take the antiderivative of this, because remember we are doing an integral, take the antiderivative of this, we get sine inverse of u plus c. Sine inverse of u plus c. So now we just put the u back in, so sine inverse x over 2 plus c. And that would be your final answer. That would be your antiderivative to 1 over 4 minus x squared. I'm sorry, 1 over the square root of quantity 4 minus x squared. So just to recap. So the first step that we did here was we made that 4 into a 1 by taking out the 4. And then our second main step was we turned that x squared over 4 into the quantity x over 2 squared. And then we did our substitution. And then finally we did our antiderivative, all right? So once again, we turn the 4 into a 1, step 1. Step 2, we turn the x squared over 4 into the quantity x over 2 squared. Step 3, we use the substitution, okay? And then step 4, we did the antiderivative. And just to recall that we turned the x squared over 4 into x over 2 squared because we wanted that quantity. We wanted to know what quantity squared would give us x squared over 4, all right? Because when we did our substitution, we made that quantity equal to u, right? We made that quantity equal to u when we did this part right here, okay? So now let's take example 2. So that's what an inverse sine looks like. That's what an inverse sine antiderivative looks like. So now let's do an inverse tangent, all right? So once again, let's start off by just rewriting this as the integral of 1 over 2 plus 9x squared dx. So how do we know this is a inverse tangent? Well, just like we knew the previous problem was an inverse sine because it was 1 over the square root of 4 minus x squared, we know this is an inverse tangent because we have 1 over 2 plus 9x squared. And if we look at the derivative of inverse tangent, it's 1 over 1 plus x squared, all right? So whenever you have 1 over a quantity plus x squared, that's a pretty good giveaway that it should be inverse tangent, all right? So let's try to do the same thing. Let's try to make that 2 into a 1. So in the previous problem, we did it by factoring out a 2. So we're going to do the same thing. We're going to factor out a 2. So 1 over 2, 1 plus, so the 2 becomes 1. The 9 just becomes a 9 halves, or a 4.5, if you want to write it that way. So that's what we have here. All right. So now the next tricky part is what we were doing before. So we turn the 2 into a 1. Now we got to turn this 9 halves x squared. Okay, we got to turn this 9 half x squared into something squared. All right, something squared. Well, the x squared is obviously just going to be an x. The 9 is just going to be a 3, right? Because 3 squared is 9. And the 2 is actually going to be a little bit tricky. The 2 is going to become a square root of 2. Okay, so square root of 2 because square root of 2 squared is 2. So that's going to be our new term on the inside of that parentheses. So we're going to have now the integral of 1 over 2 quantity 1 plus parentheses 3 over radical 2x squared, close parentheses. All right. So once again, we have a 1/2, so I'm going to rewrite this as radical 1/2 times 1 over quantity 1 plus radical 3 over 2x squared dx. Okay? So now we're going to do our u substitution again. We're going to do a u substitution. So once again, we're going to make it whatever quantity is being squared, so square root of 3. Whoops. Wrote that incorrectly. I apologize. Should be 3 over radical 2. Fix that over here. Blue. So 3 over radical 2. So the derivative is just that constant, 3 over radical 2. So now we solve this in terms of dx. So radical 2 du is equal to, radical 2 over 3 du is equal to dx. Now we make our substitutions. So we put this u in for 3 over radical 2x, and we put this radical 2 over 3 du for dx. Okay, so let's do that. So let's rewrite this as the integral of 1/2 times 1 over radical 1 plus u squared, and then dx, which was radical 2 over 3 du. So let's combine these two constants. So 1/2 and radical 2 over 3. So we're going to combine those by multiplying those two. So we get the integral radical 2 over 6 times 1 over 1 plus u squared du. So we have that. This is what we were looking for right here. This is what we were looking for. We were looking for 1 over 1 plus u squared, because that's the derivative of inverse tangent. That's the derivative of inverse tangent. So now if we take the antiderivative, we get radical 2 over 6 times inverse tangent of u plus c. And now we just plug in our u. So radical 2 over 6 tangent inverse of 3 over radical 2x plus c. That would be our final answer. It looks a little bit messy, but that would be the final answer. You could quickly do the math to figure it out, but it does work. So that is inverse tangent. So you'll see that the steps are pretty similar. The steps are pretty similar that we did previously, right? Step 1, we made that 2 into a 1 on the bottom. Step 2, we made that 9/2 x squared into a quantity x squared, so 3 over radical 2 x squared. And then we did our substitution before finally just doing our antiderivative. So the steps are very similar. The only thing you have to remember is the antiderivatives, right? The antiderivative of 1 over the quantity 1 plus u squared is inverse tangent of u. So that was the only difference. So finally, let's finish it up with c. So this is going to be an inverse secant one. So let's see what we got here. So once again, if we look back to the derivative of secant, we have x squared minus 1. So let's try to make this 9 into a 1. Let's try to make this 9 into a 1. So let's just first rewrite this as 1 over x radical 4x squared minus 9 dx. So we're going to make that 9 into a 1 by factoring out a 9. So the integral of 1 over x radical. So we're going to factor out a 9. So factor out a 9 here. So 4 over 9 x squared minus 1 dx. Now, if you notice, what we have here is we have a square root of 9. So the square root of 9 is 3. So I'm going to take out that 3. So the integral of 1 over 3x radical 4/9 x squared minus 1 dx. So we turn that 9 into a 1. Check. So now if you recall, we got to turn that 4/9 x squared into some quantity x squared. So if I do it up here, okay, so 4/9 x squared, I want to turn that into some quantity squared. So that's just going to be x in there. The 4 is going to become a 2, and then the 9 is going to become a 3. So 2/3 x. The quantity 2/3 x squared is the same thing as 4/9 x squared, because you just distribute the exponent. 2 squared is 4, 3 squared is 9, x squared is x squared. So we can rewrite this in the appropriate manner. So the integral, and I'm going to write that 1 over 3 as just 1 over 3 in the front, times 1 over x. So now we have a square root. Now we have a quantity squared, so 2/3 x squared minus 1 dx. Now we're going to do our substitution like we have done previously. So u is equal to that quantity squared. So du over dx just gives us that constant, 2/3. Solving for dx, we have 3/2 du is equal to dx. Now we make the relevant substitution, so u becomes at 2/3 x. 3/2 u becomes at dx. So let's rewrite this. 1/3 times 1 over x radical u squared minus 1. What else? What am I missing here? Dx. I'm sorry. 3/2 du. All right, so let's see what we have here. The tricky part is... Oh, so if you notice here, something different happens. We still have an x in here. Which is a little bit annoying. So if you recall, this is something we've done before. We're going to turn this u and solve it for x. So u is equal to 2/3 x is the same thing, if we multiply both sides by 3/2, as 3/2 u is equal to x. So now we're also going to make an extra substitution here to get rid of this x. All right. So, and before we do that, this 3 does cancel out this 3. So it looks like we just have a 1/2 left over. All right. So let's see what we have here. We have the integral 1/2 times 1 over. So x is now 3/2 u radical u squared minus 1 du. So we have, if you notice, we have division by 3/2 here, division by 3/2, so that's the same thing as multiplying by 2/3. So let's multiply this expression by 2/3. So we have the integral of 2/3 times 1/2 is 2/6, which is just the same thing. 2/6 is just the same thing as 1/3 times 1 over u radical u squared minus 1 du. So we finally have what we wanted. The derivative of inverse secant is 1 over u times radical u squared minus 1. And that's what we have here, right? That's what we have here. And that is, that is what we wanted. This is what we wanted. So now we can finally do our math, or do our antiderivative. So the antiderivative would just be 1/3 secant inverse of u. Oh no. I guess it just decided to crash. All right, sorry about that, people. All right, so let's get back to that. It's okay. I roughly remember where I was. So we had just had, what was it? The integral of 1/3 times 1 over u radical u squared minus 1 du. So we do the antiderivative, so 1/3 secant inverse of u plus c. Put that u back in there. If I remember, let me see, what was that u? That u was, I believe, 3/2. No. Let me think. It was 2/3. 2/3 x, if I remember correctly, plus c. And we have our final answer. So it took a bit of work, but we finally got it there. So the inverse secant is definitely the trickiest of the three, but I would say it's definitely the rarest of the three. If I were you, if I were really crunched for time, the two I would at least memorize is the first two, how to find the antiderivative using inverse sine and how to find the antiderivative of inverse tangent. So these first two examples, I would definitely try to remember the inverse sine derivative, inverse tangent derivative, because those are definitely the two more likely you will see. As usual, please let me know if you have any questions. Leave a comment. Make sure to leave any questions on Google Classroom as well for the practice I will be posting, or you can always message me on the Remind app. Otherwise, I hope you guys enjoy the rest of your day, and I will see you tomorrow. Bye-bye.